application. So I have another small presentation on detecting roofs, but questions on this one maybe.
Can you go to the last map? What is the difference between this map and these ones?
This one
Yeah,
and this one. So this one is the raw results we get from the model.
Yeah.
It works at pixel level. So for each pixel, we get the satellite images of the pixel location when we extract features and we make a prediction with the model. So that's the raw output of the model.
Okay, my question is, what is the difference between this one and the use only overlap the admin 2 level on the last one? I don't know
if I overlap
Yeah.
this one and this one?
Simply overlap admin 2 level on the last one.
Overlap.
No, not this one.
On the raster.
On the raster.
On the raster, yes.
So you add the admin boundaries on
Yes,
the
only simply.
Yeah.
What
No,
is
that's
the
true.
difference?
The difference is the population. So if you have, let's take the example of Bamako maybe to do this. So if I want to know if there is a neighborhood here, I put admin boundaries here. So I have maybe 10 pixels or a bit more. I could do just put the admin boundaries and then people know the distribution. But if I want to give a score for this admin boundary, I need to aggregate these pixels together. So to aggregate these pixels together, we take the score and we do a weighted average, meaning that we multiply each pixel by the estimated population in each pixel, and then we take the average. So that if there is if there is a lot of people that live here and no one that lives here, we put more weights here than here. That's the only thing that's happening. But when we share the results, we share both. We share this map and we share this map, and depending on what usage of it you want to do, you have both products.
When you put into this model satellite data, like NDVI,
Yes.
you basically assume that there's a connection between NDVI and your target variable.
Yes. We assume, but there is the linear model is going to learn weights.
Yes.
So at national level, if it doesn't find any correlation, it's going to put a very low weight on the NDVI.
Okay, and do you check that then? That's what you showed in the other one. Because my question would be maybe in some parts it has a strong importance because in an agricultural area, good green vegetation means good, and in a town, well, it doesn't matter at all because it just means, or it means rich people because it's urban green, which is
so that's where we might consider more complex model, because at the moment this simple linear regression is just learning a relationship at the country level. So it's learning that NDVI is a strong link with food security situation, and it doesn't care if it's a city or a rural area, it looks at on average. But we are working on more complex models. So I think Rogerio where is Rogerio? He's at the back. So Rogerio has also maybe you want to talk about it, but you have experimented with you have produced this kind of high resolution maps from CFSVA data already a few years ago, and he considered what we call geographic weighted regressions. So it's more complex regressions that give a weight to where you are in the country. So each factor, so each beta you estimate in your regression, can vary in space. So the beta that you estimate for the link between NDVI and FCS can vary in space between urban and rural areas. So that's a way to consider it.
So every pixel has its own model?
More or less. I don't think you do it at the pixel level because you have so many parameters to learn, but you do it at I know, spatial level. What we do here is before making the final prediction maps, we don't only do a linear regression, we also do some interpolation, spatial interpolation with raw data. So I don't know if you're familiar with kriging techniques or things like nearest neighbor interpolation. So we combine the linear regression model with a spatial interpolation like kriging, where we use nearest neighbor interpolation, so that we try to predict what you predict in the middle is the average of the points that are around. So this takes into account the fact that within a city you have a lot of green things, so it's going to be green around, and we combine both models. But yeah, more work needs to be done on this final parts of when you get the features and you want to put them together and learn relationship. There's a strong spatial component that needs to be integrated in some way, but that's not easy because you have so many. You have to train this data. You do it at the cluster level. So if you're lucky, you have 300 clusters, 1,000 clusters, but sometimes the BSP does emergency type of assessments with maybe only 100 or 50. Well, sometimes we have 50 clusters, things like very small number of clusters. So we have very small amount of data to learn parameters. So,
and there are no models like how poverty is created. I mean, I would assume that there's no economic models. I mean, if I have the economic model that it's a rural economy.
Well, you can add a layer on that. One feature of the regression can be land use or and everything that you can find that can describe the socio-economic status of a particular region. How do you call it? The economy of the place. That can be also a feature in the model, and you can think of interaction. At the moment, it's a very machine learning approach. So put everything in the model and see if it works. But if you try to put more economic relationship between features that you think make sense, you're going to improve your predictions for sure. We have a colleague that has been working on this part and making some Gaussian regressions with Gaussian kernels for statisticians. I don't know the details here, but for people that have a strong background in statistics, you can also have Gaussian models with different kernels for spatial and non-spatial features to improve your predictions.
You mentioned that you're using like the night city lights for the model, but the night city lights are maybe like very biased for the highways. And if you are just a poor person living next to a highway, that would like give you a kind of impression that okay, you're living in a better conditioned area while actually you're living this next to a highway.
Highway, you said?
Yes, highways. Because in the night city light map, you can detect roads very clearly because of the headlights of the car.
What we do is we extract night lights at the highest resolution possible. So they are available at 100 meters. So only if you live within 100 meters from a highway, we would have this kind of bias.
Are you correcting for the roads?
No, we don't do
that kind of a pre-processing.
We don't do any we do some pre-processing on the night light for fires, because if there is a big fire somewhere, you can get a lot of night lights for a specific month. So this we do some pre-processing to make sure that we don't take this into account. But for a place that has a lot of night lights continuously, like a road, yeah, it's true. There could be some bias in the pixels around the. But yeah, the model doesn't rely only on night lights. We try to put other things to balance this. the more things.
Depends on how much weight you are giving, because I'm sure that you are giving certain weights to it.
So the weight for night lights, yeah, the model learns it by himself. If he finds a lot of strange values due to highways, it's gonna give a low weight to night lights. So it also depends on where the survey data, the ground truth survey data has been collected to learn these weights. But yeah, true. What doesn't work well is you see this map of Mali. So here we make some predictions, huh? But we didn't have any training data here. The training data came mostly from here. So we don't have ways to evaluate the model here. We evaluate the data against the ground truth, the training. So I cannot say to the country office, I don't have any estimates of how good these predictions are. For me, it's better than nothing, because you get a sense of, distance to school lights, number of night lights, and make a prediction out of it. But if you ask me to make a prediction in Mauritania with the survey data we got in Mali, I could do it, but I'm not going to do it because I think it's better to have nothing in this case, because the relationship between the features we extract and food security in Mali and Mauritania is probably very different, and I don't want to extrapolate a modeler trained in Mali, Mauritania. I don't know if I'm.
Thank you for that. There's like a couple of more things. One is like you mentioned that you're aggregating data at the elementary level boundary using the 10-kilometer pixel. Don't you think that the pixel size is too big for aggregation?
It's true.
The health of the elementary boundary also matters a lot when you are aggregating it. Because sometimes that pixel doesn't fall in that because of the inaccuracy.
So no, it's a lot of issues we have. Sometimes you can, one aggregation is going to be only 1 pixel. So, and then we take the center of the pixel, so it can have some strange things, and sometimes we don't even have any pixel. So you're right. We often, before doing the aggregation, we don't do it at 10 kilometers. We do it at 1 kilometer. We prefer. But the thing is that when we do it at 1 kilometer, we have to download much more images to put in the neural network. So it takes a lot of time, because for each pixel, we're downloading an image from Google, from Sentinel-2. We put them into the neural network to get the features. And this is very, for those that know a bit about deep learning, neural networks is very expensive computationally. So to create a map like this at 1 kilometer resolution, depending on the size of the computer I have, it might take a few days or a few hours, depending on the size of the country, of course. So there's a balance to find between the size of prediction and the granularity that you want, because maybe you don't want to. 1 kilometer is too small to make any decisions also.
Sorry, the last question.
Yeah, sure.
If you done any type of validation with the data, like taking out some sites and see that how good it can predict for that site, or like some.
So yeah, to do the validation, it's this core, and it's what we call cross-validated, meaning that we divide the ground truth data into buckets, into 5 different buckets. We hide one of the buckets. We train the model on the 4 buckets, make prediction on the last bucket, and we compare the predictions with the ground truth. So it's a way to not to be too biased, and to see how the model is behaving in data he has never seen before. But of course we have not. This is only where data has been collected. We have not done yet prediction in somewhere that no one has never been, and then send some enumerators to check how good is that. That would be the real way to evaluate out of sample predictions. We evaluate, I have another small presentation, so maybe we should stop here for questions, but I'm going to be around for the whole day, so don't hesitate. My